In this chapter, we'll discuss the chemistry of aromatic compounds. We'll focus primarily on electrophilic aromatic substitution reactions. Electrophilic aromatic substitution reactions involve reacting an aromatic ring like benzene with an electrophile to do a substitution reaction, so replacing one of the hydrogens on the aromatic ring with the electrophile. The general mechanism involves the aromatic ring, pi electrons attacking the electrophile, forming what is called a sigma complex, which is a carbocation. Note that the electrophile will add to one of the carbons of the double bond that attacked that electrophile, and the other carbon of that same double bond will have a carbocation. Base will then remove a proton from the same carbon where the electrophile attached to reform the double bond and therefore form an aromatic ring. In this chapter, we're going to look at several examples of electrophilic aromatic substitution reactions, or EAS. We're going to look at examples of halogenation, nitration, sulfonation, hydroxylation, alkylation, and acylation. We're going to look at two examples of halogenation reactions on aromatic rings. We'll start with bromination, which is when we use bromine and usually an iron catalyst like iron tribromide to replace a hydrogen on an aromatic compound like benzene with a bromine. Now note that this reaction can actually be done without the catalyst if you have a reactive enough aromatic ring. Another example would be chlorination, where we use Cl2, iron trichloride, as a catalyst, and we replace a hydrogen on an aromatic ring with a chlorine. The mechanism of halogenation is shown here. So it starts off with bromine reacting with the Lewis acid iron tribromide to break this bond between the two bromines. So one of the bromines will donate its electrons, one of these lone pair electrons, to the iron, and then that would lead to a bromonium ion, which is a really good electrophile. The aromatic ring is electron rich, so it will attack that electrophile to form the sigma complex. Note that one of the carbons of the double bond will have a new bond to bromine, the other carbon will have a carbocation. In the last step, either this intermediate or Br negative will remove a hydrogen from the same carbon where the bromine attached. That would lead to reforming the double bond and therefore reforming the aromatic ring. So overall, we have done a substitution reaction where a hydrogen is replaced by a halogen. Note that the first step is the slow step, or the rate determining step, because we're going from a very stable aromatic ring to a carbocation. And then the last step is very fast, since we're reforming the aromatic ring, which again is very stable. Aromatic rings are very different from alkene compounds. So though they both contain double bonds, alkenes tend to do addition reactions. So here's an example. A double bond will react with HCl to add a hydrogen, form a carbocation intermediate, which gets attacked by the chlorine, and then we get an addition product. In the cases of aromatic rings like benzene, although they contain double bonds, those double bonds will generally do substitution reactions rather than addition reactions. So as an example, when they react with bromine, they'll form a sigma complex, which is essentially a carbocation, very similar to the carbocation we have here with an alkene. But the end result is, instead of the nucleophile attacking that carbocation, instead we remove a hydrogen and we get a double bond in the aromatic ring back. So the reason why our aromatic compounds are very different in reactivity than alkenes is because the aromatic ring is very stable. So rather than doing a addition reaction, we want to keep that aromatic ring, so we do a substitution reaction instead. Halogenation reactions are used in our thyroid gland to make tyrosine, which is a thyroid hormone. So the biosynthesis of this hormone involves using tyrosine, which is an amino acid that reacts with a iodine electrophilic source. So this aromatic ring, this phenol, will attack the iodine, and we do two substitution reactions, or two electrophilic aromatic substitution reactions. And then after a few other reactions, the thyroid hormone is synthesized. The next electrophilic aromatic substitution reaction that we'll talk about is the nitration reaction. So this reaction involves reacting an aromatic ring with nitric acid to add a nitro group. Usually this reaction will be slow if we do it simply with nitric acid, so we often throw in a catalytic amount of sulfuric acid, which will speed up the reaction. The purpose of sulfuric acid is to help convert nitric acid into the electrophile. So the first step is for this oxygen to react with one of the protons in sulfuric acid, and now that oxygen becomes protonated, and it allows that oxygen to be eliminated as a water molecule. So we form the double bond here by eliminating the water molecule, and we make nitronium ion, which is a great electrophile. That electrophile reacts with an aromatic ring to make the sigma complex, which then reacts with water to remove this hydrogen, form or reform the double bond, and therefore reform the aromatic ring. The nitration reaction provides a two-step procedure to make amino substituted aromatic rings. As an example, if we start off with benzene and we add nitric acid and a catalytic amount of sulfuric acid, we can add a nitro group, and then we can reduce that nitro group by a number of methods, one of them being hydrogenation, so H2 and palladium on carbon will reduce the nitro group into an amino group. Similar to any other functional group that can be reduced in chemistry, nitro groups can be reduced by three methods, one of them being hydrogenation, another one being metal reduction, which I'll show here. So a nitro group, if we add either tin, iron, tin dichloride, and combine that with an acid like ACl, we can reduce that nitro group into an amino group. A third method to reduce nitro groups, which is another method that is often used to reduce other functional groups, is a hydride reduction. So using, for example, lithium aluminum hydride will reduce a nitro group into an amino group as well. Our third example of an electrophilic aromatic substitution involves sulfonation reactions. Starting off with benzene or other aromatic rings, we can add sulfuric acid and heat it to add a sulfonic acid group and water as a byproduct. Now note that this reaction is reversible, unlike other electrophilic aromatic substitution reactions. We'll discuss the reverse reaction in a later slide, but essentially we can start off with a sulfonic acid, add water, heat it with sulfuric acid to remove that sulfonic acid functional group. Here's the mechanism for the sulfonation reaction. It starts off with sulfur trioxide, which, by the way, is made by reacting two molecules of sulfuric acid. So when the two react, an OH group is removed from a sulfuric acid to make this sulfur trioxide. Sulfur trioxide is often used in the mechanism as the electrophile, but in this case, we're going to use a protonated version of it. So sulfur trioxide will react with sulfuric acid to form this protonated version of sulfur trioxide. Then the double bonds, or one of the double bonds in the aromatic ring, will attack the sulfur, which is a good electrophile because it has that positive charge. It will break this double bond to attach the sulfonic acid group. And then base, which can be water or the conjugate base of sulfuric acid, for example, will remove this hydrogen, reform the aromatic ring, as you see here in the product. So I mentioned previously, sulfonation reactions are reversible. So here is the reaction backwards, called a desulfonation reaction. Starting with a sulfonic acid, if we add water, sulfuric acid, and heat it, we can remove that sulfonic acid functional group and go back to the benzene molecule. Sulfonic acid functional groups have a lot of applications. One of them is that it is used as an organic acid. We have seen many examples of sulfuric acid being used as an acid, like for example as an acid catalyst. And sulfuric acid is one of the strongest acids we have in chemistry. It has a pKa of -9. It is, of course, water soluble. However, many sulfonic acids are also used as organic soluble acids. As an example, para-toluene sulfonic acid, which is shown here, has a pKa of -2.8, so almost as low as sulfuric acid. But it has one advantage over sulfuric acid, and that is it is organic soluble due to this toluene group. Unlike sulfuric acid, sometimes some reactions, because it's not organic soluble, the reaction will be a little slow. With para-toluene sulfonic acid, you won't have that issue. You can dissolve it in most organic solvents. The chemistry of sulfonic acids is very similar to carboxylic acids. For example, if we react para-toluene sulfonic acid with ionyl chloride, we can replace the OH group with a chloride and form para-toluene sulfonic chloride, or tazo chloride. This will behave very similar to an acid chloride. For example, if we react it with an alcohol, the alcohol will replace the chlorine. So here's the structure of tazo chloride. The oxygen will attack the sulfur, eliminate the chlorine to get a sulfonic ester, which of course is very similar to a typical ester. Tazo chloride can also react with an amino group to form a sulfonamide. Sulfonamides, or sulfur drugs, were the first effective antibiotic that was introduced into the market. They were introduced around 1934. Sulfur drugs are effective as antibiotics since they mimic para-aminobenzoic acid, which is a compound that is necessary for bacterial growth. The Friedel-Crafts alkylation is a reaction between aromatic compounds and a alkyl halide. Typically, this reaction is done with a Lewis acid, like aluminum trichloride, to add an alkyl group. Now, note that alkyl groups are electron donating groups, and so they generally make their product, so this product here, more nucleophilic than benzene. That means Once you form the product, this is more likely to react with the electrophile, which is this alkyl halide, rather than benzene. So we have to use an excess of benzene in order to make sure that we only get one substitution of their alkyl group. Otherwise, the product that we get will often have multiple alkyl groups. Another side note about this reaction is that we can use primary, secondary, or tertiary alkyl halides. However, primary and secondary alkyl halides very often rearrange since they are turned into carbocations, and those carbocations will often do alkyl shifts or hydride shifts to form more stable carbocations. The Craft alkylation reaction starts off with an alkyl halide reacting with aluminum trichloride. So the chlorine has lone pairs, and so it's a Lewis base that will react with aluminum, which is a Lewis acid. It'll donate electrons to the aluminum, and then this bond will break, forming a carbocation where the halogen was attached. That carbocation will be the electrophile in this electrophilic aromatic substitution reaction. The benzene ring or other aromatic ring will attack that carbocation, form the sigma complex, and then a base such as aluminum tetrachloride or Cl- will remove this hydrogen, reform the double bond, giving us the aromatic ring again. The first step will be slow since we're breaking the aromatic ring. The last step will be fast in comparison since we're reforming the aromatic ring. In electrophilic aromatic substitutions, in general, substituents have a large effect on how reactive the aromatic ring will be. Electron donating groups in general, such as alkyl groups, will make the aromatic ring more reactive towards electrophilic aromatic substitution reactions, since the ring will be more electron rich, which means it's a better nucleophile. It also means that the carbocation in the sigma complex will be stabilized. Electron withdrawing groups, such as carbonyl compounds, for example, aldehydes, ketones, carboxylic acids, and esters, or other electron withdrawing groups like nitro groups, nitriles, sulfonic acids, quaternary nitrogen atoms that have a positive charge, or even any amino group, since these amino groups usually in the Friedel-Crafts alkylation will react with aluminum trichloride to form a complex that has a positive charge on the nitrogen. All of these functional groups are electron withdrawing, and in generally they affect the Friedel-Crafts alkylation reaction so much that they generally do not allow the reaction to occur. As far as electron donating groups, in the Friedel-Crafts alkylation reaction, as we mentioned before, they tend to speed up the reaction so much that the typical product that we get, the alkylated benzene product, would be more reactive than benzene. And so we usually use an excess of the reactant in order to avoid adding multiple alkyl groups to it. In the Friedel-Crafts alkylation reaction, we could use primary, secondary, and tertiary alkyl halides. However, when we use primary and secondary ones, we can often see rearranged products from carbocation rearrangements. As an example, if we use this primary alkyl halide, not only do we get the expected product, which would be butylbenzene. So if we aluminum trichloride removes this chloride, we form a carbocation at this carbon. And if that gets attacked by the ring, we get this product. However, the major product in this reaction is actually sec-butylbenzene, which would be formed from a hydride shift. So this is the initial carbocation after the chloride is removed. It's a primary carbocation, which can undergo a hydride shift so that adjacent carbon has a hydrogen that can shift over with the electrons in that bond, forming this secondary carbocation. And if that secondary carbocation is attacked by benzene, we will get the rearranged product we see here. Second example is involving this primary alkyl halide. Once we remove the chloride, we have a primary carbocation shown here, which can undergo an alkyl shift. So one of these three methyl groups can shift over since it's on the adjacent carbon, along with electrons in that bond to form this rearranged product, which has a carbocation now at a tertiary carbon. The methyl group that was on that carbon shifted over to the CH2 group. If benzene attacks this carbon, we get the rearranged product we see here. A related reaction to the Friedel-Crafts alkylation is the Friedel-Crafts acylation. This time, instead of using an alkyl halide, we use an acid chloride. Using an acid chloride in an aromatic ring plus aluminum trichloride, and if we heat it, we can attach the benzene ring to the carbon that has the halogen and end up with a ketone. Notice that the product that we get from this reaction has now an electron withdrawing group on the aromatic ring, which means the product is less reactive than benzene. So doing the Friedel-Crafts acylation solves the issue of having to use an excess of benzene, which we had to do in the alkylation reaction. A second advantage of using the Friedel-Crafts acylation over the alkylation is that we don't see rearranged products in the acylation. Here's an example of how that plays out. If we have a primary alkyl halide, if we add aluminum trichloride to it, instead of getting a substituted product that has a propyl group, we get this isopropyl group. And that would be a result of a rearranged product that leads to, so it starts off with a primary carbocation rearranging through a hydride shift. So if this hydride moves over to this carbocation, we will now have a secondary carbocation, and if that gets attacked by benzene, we end up with this isopropyl group instead. In order to avoid this rearranged product, if we really wanted to have a normal propyl group attached to the benzene, we can go around it by doing an acylation reaction with the appropriate acid chloride. So it has to have 3 carbons as well. Add aluminum trichloride. We end up with this as a product. And if we reduce this carbonyl by a Clemmensen reduction or a Wolff-Kishner reaction, we can remove that carbonyl and end up with a propyl group there. So combining the acylation plus the reduction of the ketone will give us the product that we're looking for. The mechanism for the Friedel-Crafts acylation involves the aluminum trichloride pulling off the halogen. So this halogen and its electrons will attack the aluminum. That will lead to breaking this bond, forming what's called an acyl-cation, which has 2 resonance forms. So if we move one of these lone pairs to make a triple bond here, get rid of the positive charge on the carbon, we get this acyl-cation, the resonance form. Either of these 2 resonance forms is electrophilic at the carbon, which would be attacked by benzene, adding the ketone. Then a base, such as aluminum tetrachloride or Cl minus, will remove this hydrogen and reform the double bond, and therefore reform the aromatic ring. Vitamin K1 is a coenzyme required for blood clotting. In the biosynthesis of vitamin K1, a Friedel-Crafts alkylation is used to form or add an alkyl group. This carbocation will react with this aromatic ring, forming this intermediate, which then loses a hydrogen, reforming the double bond to give us the Friedel-Crafts product. In this question, we want to identify the reactants in the Friedel-Crafts acylation reaction that will lead to this ketone. In a Friedel-Crafts acylation reaction, we generally react a benzene or other aromatic ring with an acid chloride to form a ketone. So in thinking about this reaction backwards, we want to, since we're dealing here with a symmetrical ketone, it doesn't matter which aromatic ring we break off, we're going to have the same reactant. In both cases, we would have to use benzene and the following benzoyl chloride reactant. Now that we have covered several examples of electrophilic aromatic substitution, let's take a look at how substituents affect the reactivity of the aromatic ring in electrophilic aromatic substitution reactions. We'll use the nitration reactions as an example. Note that when we have just a benzene ring, so that would be the first entry here, the relative reactivity or relative rate of reaction is 1. When we introduce a methyl group there, so in other words, we're using toluene, the reaction is almost 25 times faster. When we use phenol, the reaction is about 1,000 times faster, so we consider a methyl group and a hydroxyl group activating groups. In other words, they speed up the reaction. They activate the aromatic ring in terms of the electrophilic aromatic substitution reaction. A halogen, like chlorine, will deactivate the aromatic ring, so it is much slower when we use a chlorine on benzene. And when we use a nitro group, the reaction is even slower. So both a halogen and a nitro group are deactivating groups in terms of the electrophilic aromatic substitution reaction. Electron donating groups or activating groups are generally going to make an aromatic ring more electron rich. And so that means that the ring would be more nucleophilic. It also means that the carbocation in the sigma complex is more stabilized. It also means that the activation energy will be lower for the rate determining step, which is the formation of the sigma complex. Deactivating groups, which are electron withdrawing groups, will do the opposite. They will make the ring less electron rich, which means it will be less nucleophilic. It also means that the carbocation or the sigma complex will be destabilized or higher in energy, which will lead to a higher activation energy for the rate determining step. There are many function groups that can be added to an aromatic ring, which will affect the reactivity of that aromatic ring. In general, alkyl groups and other phenyl groups will make the ring activated. Other atoms that have lone pairs in general will make the ring also activated, more so than alkyl groups. So for example, a methoxy group, an amino group, a phenol group, an ester or an amide that has a nitrogen or an oxygen directly attached to the aromatic ring will also activate the ring. Halogens in general will deactivate the aromatic ring. Carbonyl functional groups or other highly electron withdrawing groups will deactivate the ring as well. So the reactivity goes in this direction where these are the functional groups that make the ring even more reactive, and these will make it less reactive. Let's now go through several examples of functional groups and how they are categorized as far as activation of the aromatic ring. Functional groups that have an oxygen or a nitrogen directly attached to the ring will generally be considered strongly activating groups. For example, phenols, amino groups, ethers, and other substituted amino groups. Although these have highly electronegative atoms, which you would think would make the ring less electron rich by withdrawing electron density, they're actually considered electron donating through resonance. The phenol, as an example, can donate electron density into the ring as shown here. So the lone pair can push electron density specifically to the ortho and para positions. So one of the resonance forms shown here will have a negative charge at that ortho position, which we can draw another resonance structure which will place that negative charge at the para position or at the other ortho position. Again, these functional groups make the ring more electron rich, which means it's more nucleophilic. It means that the carbocation intermediate is more stabilized, and it means that the activation energy for the rate determining step is lower. Esters and amides are considered moderately activating groups as long as the oxygen or the nitrogen is directly connected to the aromatic ring. Although we have a highly electronegative atom like oxygen or nitrogen, which are considered electron withdrawing groups in general, these are overall electron donating groups because of resonance. So very similar to the phenol example, the lone pair on this oxygen can donate electron density towards the ring. Same thing for the lone pair on this nitrogen, which can donate electron density into the ring. Alkyl groups or phenyl groups are considered weakly activating groups, and they do this primarily through hyperconjugation. So when you have a methyl group, for example, in the sigma complex, one of the resonance structures will have a positive charge directly on the same carbon as the substituent, in this case a methyl group. That would lead to stabilizing that carbocation through hyperconjugation, compared to an example where we don't have that methyl group, instead we have a hydrogen. That would be a less stable carbocation. Halogens in general are considered weakly deactivating groups. Fluorine is too highly electronegative to be able to donate electron density through resonance like an oxygen or a nitrogen in phenol and aniline. The other halogens don't match orbitals very well since they're lower in the periodic table, and so they are not able to donate electron density into a carbon, which would be a part of the aromatic ring. So overall, the halogens, although they have lone pairs like oxygen and nitrogen, because they're electronegative or more electronegative, or they are too big of an atom, they're generally not able to donate electron density into the ring as well as oxygen and nitrogen. Carbonyl compounds are considered moderately deactivating, for example, aldehydes, ketones, esters, carboxylic acids, and amides. Note that we previously talked about how esters and amides are activating groups, but that is only when the oxygen or the nitrogen of these functional groups are directly connected to the aromatic ring. When it is the carbonyl that is connected to the aromatic ring, they're considered deactivating groups. Other groups like nitriles, nitro groups, quaternary ammonium groups, and sulfonic acids are considered strongly deactivating. All of these groups are deactivating through both induction as well as resonance. Using the ketone as an example, it is deactivating because we have highly electronegative atoms like oxygen. And also because of resonance, if we draw a resonance structure that pushes electrons towards the oxygen of the carbonyl, we create this resonance structure that has a positive charge at either the ortho or at the para position. Substituents on an aromatic ring not only affect the speed of the reaction, in other words, some of them are considered activating while others are deactivating groups, but they also affect the orientation of a new substituent whenever we do an electrophilic aromatic substitution reaction. As a rule of thumb, activating groups are generally going to give you mostly ortho and para substitution, while deactivating groups will give you primarily meta substitution. The one exception to that rule is halogens, which are considered weak deactivators. They will also give you ortho and para substitution. Here's an example involving nitration. When we use moderate and strongly deactivating groups like carbonyls and nitro groups and nitriles, we see primarily meta substitution. When we use the halogens, which again are weak deactivators, these give you primarily ortho and para substitution. As you can see by these examples, primarily ortho and para substitution. And moderate, weakly, and strong activators will all give you primarily ortho and para substitution, as you can see by these examples. As mentioned before, in general, all activating groups will give you primarily ortho and para substitution. So as an example, an ethyl group, which is considered a weak activating group, will give you primarily ortho substitution when we do a chlorination, as well as para substitution. Deactivating groups in general will give you meta substitution. This is especially true for moderate and strongly deactivators. So a nitro group, which is a strong deactivator, when we do a halogenation like bromination, we would get primarily meta substitution. The exception to that rule is that weak deactivators, which are the halogens, will generally give you ortho and para substitution. As an example, if we had a chlorine and we did a nitration, we're going to get primarily ortho and para products. Let's look now at the reasons why certain functional groups will give you primarily ortho and para substitution, while others will give you primarily meta substitution. We'll start with weak activators, for example, alkyl groups. These are primarily ortho-para directing. The reason for that is one of the resonance structures that is formed from ortho substitution has a highly stable carbocation, which has the carbocation directly on the same carbon as the methyl group. The same thing occurs in para substitution. One of the resonance structures, so there are three, one of the resonance structures is highly stable because we have a carbocation that is on the same carbon as the methyl group. When we do meta substitution, which rarely occurs, we never have a resonance structure that has the carbocation directly where the methyl group is. So we don't have a highly stable carbocation intermediate, therefore meta substitution does not occur, or at least not to the same extent as ortho and para substitution. When it comes to the moderate and strong activators, which would be, for example, phenol, we generally see ortho and para substitution. The reason for that is when we do ortho substitution, we have an extra resonance structure. So there are 4 versus 3 that we see in meta substitution. One of those 4 resonance structure when we do an ortho substitution also has a full octet on every atom. So the oxygen and carbon, as well as every other carbon in the ring, has a full octet. That makes this a very stable resonance structure, more so than the other ones. We see the same thing with para substitution. We have 4 resonance structures. Generally, when we have more resonance structures, that pathway would be more likely to occur. Also, one of the resonance structures has a full octet on every atom that is part of the molecule, and so this is a highly stable resonance structure. You might recall that the weak deactivators, which would be the halogens like a chlorine, are generally ortho-para-directing, even though they are deactivating groups. Very similar to the phenol example, when we do an ortho or para substitution, we're going to have 4 resonance structures. In the case of a meta substitution, we get 3 resonance structures. So again, in general, the more resonance structures we have for very similar intermediates, the more stable that resonance or that intermediate will be. In addition, one of the resonance structures when we do ortho or para substitution is highly stable because there's a full octet on every atom. Moderate and strong deactivating groups are generally going to direct a new substituent to the meta position. The reason for this is when we do ortho or para substitution, we're going to end up with a carbocation intermediate that has a resonance structure that involves a carbocation directly attached or on the same carbon as the strongly deactivating group, so the highly electronegative group. For example, with an aldehyde, if we did an ortho substitution of a nitro group, we're going to have this positive charge on the same carbon as the carbonyl. So this is a very unstable resonance structure. We have a similar resonance structure when we do para substitution, where the positive charge is on the same carbon as the carbonyl. In the case of meta substitution, the positive charge will always be away, at least one carbon away from the carbonyl. With substituents that direct a new substituent to the ortho and para position, we generally end up with 2 possible products. The exact ratio between these 2 products will depend on the substituents. For example, if we have a methyl group already on the benzene ring and we try to do a nitration, we're going to get approximately a 2-to-1 ratio between the ortho and para product. Notice that this is based on primarily statistics. So there are 2 ortho positions, there's only 1 para position, so it makes sense as long as both the existing functional group, which is the methyl, and the new substituent are relatively small. In other words, they both have very low sterics. The ratio of the products between ortho and para should be relatively close to a 2-to-1 ratio. As the size of the existing groups increase, for example, if we replace the methyl group with an ethyl group, the ratio will go down closer to being a 1-to-1 ratio, or in some cases, preferring the para substituted product. So with an ethyl group, we get a 1-to-1 ratio between ortho and para products. With a curved-butyl group, since it's such a large group, it blocks the ortho position to some extent, and we get primarily para substitution. In this question, we're going to predict the 3 possible isomers that would occur from the monobromination of toluene, and then we're going to predict which is the most likely product from the 3. This question is basically asking us to draw the ortho, the meta, and the para substituted products once we add bromine to toluene. So Br2 and iron tribromide would add a bromine to either the ortho, meta, or para position, and giving us these three isomers. Since a methyl group is a weak activating group, generally it's going to direct any new substituent to the ortho and para position. So the primary products should be the ortho and the para products. And if I had to guess, since bromine and a methyl group are relatively small groups, I would suspect that the main product would be the ortho product in this example. In this question, we're going to try to predict the major product from the nitration of bromobenzene. Bromobenzene has a weak deactivating group, which is a ortho-para directing group. So when we do a nitration of bromobenzene, we should expect primarily ortho and para substitution. Since the nitro group and the bromine are relatively small, I would suspect that the ortho substituted product would probably be the major product. In this question, we're going to try to explain why the Friedel-Crafts alkylation often gives multiple substitution products, but the Friedel-Crafts acylation does not. And there's an example shown here with benzene and methyl chloride. When we do an alkylation, we get a single substituted product as well as a disubstituted product. When we do an acylation, we get only a single substituted product. You might recall that alkyl groups, like a methyl group, are activating groups. They're weakly activating groups. And so the product from this reaction is actually more reactive than benzene since it has an activating group on the benzene ring. So it makes sense that once we do a single alkylation, the product would continue to do other alkylation reactions as long as there's enough alkyl halide and the acid catalyst. So that explains why we not only do we get a single alkylated product, but a product that has two alkyl groups. When we add a acyl group or a ketone, this product is now less reactive than benzene since it has a deactivating group, a moderately deactivating group. And so the product that we see here is not going to want to do another substitution since it's less reactive than benzene. This question is asking us to do a synthesis of metachloronitrobenzene from benzene. In order to synthesize metachloronitrobenzene from benzene, we would have to do a chlorination and a nitration. Often when we do one of these synthesis examples involving a substituted benzene compound, we want to think about what each functional group does in terms of directing the new substituent. And so we want to obviously do a nitration and a chlorination, but we have to choose one of them first, perhaps, since the other one may lead to the wrong isomer product. If we do a nitration first, we would add a nitro group, and you might recall that the nitro group is a meta-directing group, and so the chlorine would add to the meta position, giving us the desired isomer. However, if we try to do a chlorination first, the chlorine, you might recall, is an ortho-para directing group. So if we do the nitration after the chlorination, then we would end up with an ortho or a para substituted isomer instead. In this question, we want to explain why acetylide, which is the molecule shown here, is less reactive than aniline towards electrophilic aromatic substitution? So this question is asking us to explain why acetylide, which is the molecule shown here, is less reactive towards electrophilic aromatic substitution than aniline. Aniline, you might recall, is a compound that has benzene with an amino group attached to it. Now, there are many ways to explain the reactivity, the difference in reactivity between acetylide and aniline. One of the ways is that the lone pair on the nitrogen can donate electron density into the ring as shown here, and the negative charge that is created in the ring can be moved around the ring through other resonance structures. We would do something similar with aniline. The difference is that the lone pair on the nitrogen of acetylide is actually also tied up in resonance with the carbonyl of the amide. So we can draw another resonance structure which involves moving the electrons towards the carbonyl to create this other resonance structure. We wouldn't do this with the aniline. And note that this structure, this resonance structure, is actually more stable since we have a negative charge on the oxygen compared to the other resonance structures that we see here with a negative charge around the carbons. So in the case of acetylide, the lone pair is actually tied up in resonance with the carbonyl, while in the case of aniline, that lone pair, since there is no carbonyl, is free to push electron density into the ring, which makes the ring even more electron rich than it would be in acetylide. We're now going to look at a few examples of di-substituted benzene compounds when we involve them in the electrophilic aromatic substitution reaction. When we have multiple substituents already on the ring, predicting the product can be challenging. However, when the two groups are directed to the same position, it is fairly easy to predict the product that we're going to get. For example, if we have a methyl group para to a nitro group on benzene, since both substituents direct to the same two spots in the benzene ring, the product is very easy to predict. In the case of the methyl group, it's an ortho-para directing group, and so it would be directing a bromine to the ortho position to it, which would be these two carbons here. The para position is blocked because of the nitro group, so there's only two possible places to direct a new substituent. Nitro groups, remember, are meta-directing, and the meta position is actually the same two carbons that the methyl group wants to direct the bromine to. So the bromine, since both the methyl and the nitro group are directed to the same spot, will be located now in the product in this carbon. Because of the symmetry, it doesn't matter whether we put the bromine on the right or the left side of the molecule. When we have a di-substituted benzene compound and both groups are not directed to the same location, then generally the new substituent will go on benzene based on the strongest activator. For example, if we have a phenol in a methyl group, the phenol is the stronger activator, and so it's going to direct the new substituent, which is a nitro group, ortho to it, since the para position is blocked. So that would be directing to these two carbons. Note that the methyl group is also an ortho para directing. The ortho positions are these two carbons and the para position is blocked. But because the phenol is a stronger activator, it's going to predict where the nitro group will add, which would be ortho to it. And so this is the major product that we should get from this reaction. Something else to keep in mind is that a carbon on a benzene ring between two substituents is generally too hindered of a location to add any new substituents there. As an example, if we have metachlorotoluene, the methyl group, you might recall, is a weak activator, while the halogen is a weak deactivator. So the methyl group should direct the new substituent, ortho or para, to it. Notice that one of the ortho position is blocked by the fact that there are two substituents surrounding it. So the halogen is very likely to add to the para position of the methyl as well as the ortho position of the methyl. Very little of this product, which has the halogen in between the two substituents, will form. And compare that to an example where we have a methyl and a nitro group ortho to each other. If we do a halogenation, because the methyl group is a stronger activator than the nitro group, it would direct the new substituent, ortho or para, to it. Here's an example where we have a meta-substituted compound with bromine and a methoxy group, and we want to predict the product from electrophilic aromatic substitution of this compound. If we try to do electrophilic aromatic substitution on this meta-substituted benzene compound, the electrophile should add ortho and para to the methoxy group, which is a stronger activator than the bromine. So the electrophile should end up ortho or para to the methoxy group. Note that it's very unlikely that we're going to get a substituent in between the two groups. Although that's an ortho position to the methoxy group, it is blocked by the sterics of these two substituents. In this question, we want to predict the product from the bromination of para-methylbenzoic acid. Para-methylbenzoic acid has a weak activating group in the methyl group, and it has a moderately deactivating group in the carboxylic acid. The methyl group is a stronger activator, so it should predict where the bromine adds. It should add ortho to the methyl group since the para position is blocked by the carboxylic acid. So this product here should be the major product. We want to synthesize 4-bromonitrotoluene from benzene. The compound we're trying to make has a bromine at the 4 position, a nitro group at the 2 position, and it has a methyl group at the 1 position. We're going to start off from benzene. So we're going to be adding 3 different substituents, and we need to think about which one we want to add first and which one we want to add last based on how these groups direct a new substituent to the benzene. In this question, we're trying to synthesize 4-bromo-2-nitrotoluene from benzene. In the process, we're going to add 3 new substituents, and so we want to think about how or what sequence we would add them in so that as we add any new substituents, they're directed to the correct position. If we try to do the alkylation first through a Friedel-Crafts alkylation, which involves methyl chloride and aluminum trichloride, we can make toluene, and then a bromination should add the bromine to either the ortho or para position, since the methyl group is an ortho-para director. That should give us a way to make para-bromotoluene, although this is not the best route to make this compound, since you might recall that because both the methyl group and the bromine are relatively small groups, I would suspect that this reaction should give you primarily the ortho substituted product rather than the para substituted product. But we'll ignore that for this synthesis. Another way to make the same compound would be to switch the order of these two substituents, how we add them. We could do the bromination first to give us bromobenzene. The bromine is an ortho para directing group, so it should add the methyl group to either the ortho or the para position. And again, I would suspect that this reaction should give us primarily the ortho substituted product, but it does give us a way to make the para substituted product. From para bromotoluene, we could do a nitration to add the nitro group to the correct position. Since the methyl group is a stronger activator than the bromine, it should direct the nitro group to the ortho or the para position. But because the para position is blocked, the nitro group will add to the ortho position. Notice that this compound is symmetrical, so it doesn't matter which ortho position we add them to, it should give you the same product. Another possibility that you might think about would be to add the nitro group first and then do the alkylation or bromination next. One of the problems we're going to run into is that the nitro group is a strongly deactivating group. You might recall that the Friedel-Crafts alkylation and acylation is a little finicky in that we can't do the reaction with an electron withdrawing group already existing on the ring. And so we want to save this nitro group to the end to avoid issues with the Friedel-Crafts alkylation. Another important reaction involving aromatic rings is called the nucleophilic aromatic substitution reaction. So you might recall from the the first part of this chapter that aromatic rings are generally considered nucleophiles and they can react with electrophiles in the electrophilic aromatic substitution reaction. However, under the right conditions, they can also react with nucleophiles. Before we get into that, let's discuss what would happen if we had an aromatic ring with a halogen leaving group and we try to do an SN2 reaction. You might recall from previous chapters that this reaction generally does not occur. So if we add the hydroxide ion and try to do an SN2 reaction, there should be no reaction, since in an SN2 reaction, the hydroxide ion would have to get inside of the ring to do a backside attack of this carbon to leaving group bond. And so no reaction would occur since that backside is blocked by the ring. However, if you put enough electron withdrawing groups on the ring, for example, several nitro groups, that activates that carbon to do another type of substitution reaction called nucleophilic aromatic substitution. This is a reaction that occurs through a different mechanism and it does not involve backside attack of the carbon to halogen bond. A hydroxide ion, for example, can replace the halogen through a nucleophilic aromatic substitution, again, if we have several electron withdrawing groups on the ring. Let's look now at the mechanism for nucleophilic aromatic substitution reactions. The nucleophile, for example, the hydroxide ion, would generally attack the same carbon as the halogen, lead to breaking this double bond and putting a negative charge on the carbon that is directly attached to the nitro group. This intermediate is called the Meissenheimer intermediate or complex. This negative charge would then reform the double bond by eliminating the leaving group. Note that this reaction is very similar to the addition of a nucleophile to the beta carbon of an alpha-beta unsaturated carbonyl. For example, if we had a compound like this with an electron withdrawing group, and this could be a nitro group or a carbonyl, like a ketone. Generally, nucleophiles will add to the beta carbon, similar to their nucleophilic aromatic substitution reaction. You might recall this is the alpha carbon and this is the beta carbon. So this reaction is very similar to the conjugate addition to alpha-beta unsaturated carbonyls. The reaction is faster when we have electron withdrawing groups on the ring, especially ortho and para to the leaving group. As you can see by this intermediate, this negative charge forms at the ortho position of the leaving group. So having an electron withdrawing group like a nitro group here really stabilizes that intermediate. If we have it at the para position through another resonance form, we can also stabilize the same negative charge. As mentioned on the previous slide, having an ortho or a para substituted aromatic ring with a leaving group is beneficial for the nucleophilic aromatic substitution reaction. For example, having an ortho nitro group, after the nucleophile adds to the same carbon as the leaving group, as it usually does, it leads to the Meissner-Heimer complex, which has a negative charge on the carbon where that nitro group is, which is able to now stabilize that negative charge through resonance as shown here. After that negative charge reforms the double bond, by eliminating the halogen, we get a product from this reaction. The para-substituted nitro compound would do the same thing. So when the nucleophile adds to the same carbon as the leaving group, we form a Meissner-Heimer complex with a negative charge here. However, through resonance, we could move that negative charge to the same carbon where the nitro group is. That allows that negative charge to be stabilized. And once we reform the double bond by eliminating this leaving group, we can get to the product. When the nitro group is meta, the nitro group will be less helpful in stabilizing the Meissner-Heimer complex. As you can see here, when the nucleophile adds to the carbon with the leaving group, we form the Meissner-Heimer complex, which has a negative charge on that carbon. If the nitro group is at the meta position, it's not able to stabilize it as much. So at least at this temperature, 130 degrees Celsius, which is the same temperature we use for the ortho and the para substituted in reactants, the reaction will not occur for the meta substituted compound. In general, the more electronegative a halogen is, the better the leaving group it is for the nucleophilic aromatic substitution reaction. This is very different from most typical substitution reactions involving halogens as leaving groups. In general, for example, for the SN2 reaction, the iodine would be a better leaving group than the fluoride. This is the exact opposite of what we see for the nucleophilic aromatic substitution reaction. This can be explained by the fact that the more electronegative the halogen is, the better the Meissner-Heimer complex is stabilized. As we increase the number of electron withdrawing groups around the aromatic ring, the faster the nucleophilic aromatic substitution reaction occurs. As an example, if we have a nitro group at the ortho position of this halogen, if we try to do a substitution with sodium hydroxide, we can do it at about 150 degrees Celsius and replace the chlorine with a hydroxyl group. We can lower the temperature when we add a second nitro group, one at the ortho and one at the para position, and do the same type of substitution reaction. When we add 3 nitro groups 2 at the nitro position, ortho positions, and 1 at the para position, we can do the reaction at room temperature. Note that adding electron withdrawing groups at the meta position does help the reaction in terms of speeding it up, but it doesn't have as much of an effect as it would if we place them ortho or para to the leaving group. There are many nucleophiles that can be used, as well as many electron withdrawing groups that we can use in this reaction. For example, we could use ammonia as a nucleophile and replace a bromine. Notice this example involves a nitrile in a nitro group, ortho and para to the halogen. We could use a methoxy group to replace a fluorine, and we can have a ketone as well as a nitro group as electron withdrawing groups. We're now going to do a quick comparison between electrophilic aromatic substitution reactions and nucleophilic aromatic substitution reactions. In general, electrophilic aromatic substitution reactions are favored by electron donating groups, which activate the ring because they make the ring more electron rich, which makes it into a better nucleophile. It also stabilizes the sigma complex. Electron withdrawing groups will cause the opposite, so they generally deactivate the ring. They make it less reactive. Electron withdrawing groups generally are meta-directors, with the exception of halogens. Electron donating groups would be generally ortho-para directing groups. In the electrophilic aromatic substitution reactions, a hydrogen is replaced by a substituent. Nucleophilic aromatic substitutions reactions are generally favored by electron withdrawing groups. Generally, electron withdrawing groups will cause the ring to be more reactive since they stabilize the Meitner-Heimer complex. Generally, electron withdrawing groups need to be at the ortho and para position to have the most effect. So in a sense, they're ortho and para directing in terms of the new substituent replacing the halogen. And the reaction overall will involve a nucleophile replacing the leaving group, typically a halogen. Here's a reaction that has been used in order to make a herbicide shown here. The reaction involves an aromatic ring with a halogen, and it's going to react with a phenol ring that also has a halogen. The reaction involved to make this herbicide is a nucleophilic substitution reaction, which involves taking the phenol and turning it into the conjugate base by adding potassium hydroxide. The phenol, or the conjugate base of the phenol, is a good nucleophile that can add to the carbon that has the fluoride, which is a very good leaving group for the nucleophilic aromatic substitution reaction. This ring is activated for the nucleophilic aromatic substitution reaction by the fact that it has a para-nitro group, as well as having this fluoride, which is a very good leaving group for this reaction. After the addition of the phenoxide ion to this carbon, we have created the Meitner-Heimer complex, which will then proceed to eliminate the fluoride and reform the aromatic ring. Let's go over a few more reactions that aromatic rings undergo, one of them being the reduction of the aromatic ring. You might recall that double bonds from alkenes are very easy to remove through a hydrogenation reaction. So if we add H2 and palladium, or palladium on carbon, we can add hydrogens to that double bond and turn it into an alkane. If we also have an aromatic ring, notice that we usually don't remove the double bonds from the aromatic ring, since that aromatic ring is very stable. There are ways to reduce aromatic rings. through hydrogenation reactions, and these typically involve using high pressure of hydrogen, higher temperatures, like 100 degrees Celsius or more, or using a more reactive metal like platinum or rhodium. As an example, orthosilane can be reduced with hydrogen by using platinum, using higher pressures of hydrogen at room temperature to get rid of the double bonds of the aromatic ring and produce this cyclohexane substituted product. The next example involves using rhodium, which is a more reactive metal. We can do this with 1 atmosphere, which is basically the atmosphere pressure that we have at sea level, using room temperature to remove the double bonds in the aromatic ring and create this substituted cyclohexanol. Let's review some of the reactions we learned in this chapter. In this slide, we have a reaction here with an aromatic compound that has an alkyl group, and we're going to add nitric acid and sulfuric acid. The next example involves a substituted phenol, and we're going to add Cl2 and iron trichloride. The third reaction has phenol with orthofluorine, and we're going to do a reaction with bromine and iron tribromide. The fourth reaction will have a ketone on a benzene ring, and we're going to add sulfuric acid and heat the reaction. And the last reaction in this slide would involve an ethyl group on benzene, and we're going to add methyl chloride and aluminum trichloride. Nitric acid and sulfuric acid will lead to adding a nitro group on an aromatic ring. If we already have an isopropyl group, that is an ortho para-directing group, and so we should get primarily ortho substituted nitro as well as para substituted nitro products. Cl2 and iron trichloride will add a chlorine to an aromatic ring. If we have a phenol and a methyl group, the phenol is a stronger activator, so it should direct the chlorine to the ortho position. So at any of these two carbons, which would be the same product, the chlorine should add, and so we will have this as a product. Br2 and iron tribromide will add a bromine to an aromatic compound. So if we have an OH and a fluorine, the OH is a stronger activator. It is also an ortho para director, so we should get two products where the bromine adds para or ortho. Sulfuric acid and heat will lead to adding a sulfonic acid group to a benzene compound. Since the ketone is a meta director, the sulfonic acid should add to the meta position. Aluminum trichloride and alkyl halide should lead to a Friedel-Crafts alkylation. The ethyl group is an ortho para directing group, so we should have two products where the methyl group has ortho or para to it. We're now going to review 5 more reactions that we cover this chapter. In the first reaction, we're going to add aluminum trichloride and an acid chloride to toluene. In the second reaction, we're going to add sulfuric acid, water, and heat a sulfonic acid. In the third reaction, we're adding tosyl chloride to an amine. Then we're adding tosyl chloride to an alcohol. And then lastly, ethanyl chloride to a sulfonic acid. The first reaction shown here is an example of a Friedel-Crafts acylation involving aluminum trichloride, which will remove this chlorine from an acid chloride and allow us to add an acyl group to the ortho or para position of this methyl group. Methyl groups are generally ortho para directing, so for that reason we get the para substituted product as well as the ortho substituted product. Sulfuric acid, water, and heat will lead to the desulfonation of a sulfonic acid, so for that reason this is our product. Tosyl chloride will add a tosyl group to an amino group or to an alcohol, as we see by these two reactions. Thionyl chloride will generally replace a hydroxyl group on a sulfonic acid with a chlorine. The last two reactions of this chapter that we'll review will be these two, which involve taking an aromatic ring with a halogen and several electron withdrawing groups and adding a nucleophile to it. And then lastly, we're going to do a hydrogenation of an aromatic ring in this last reaction. The first reaction shown here is an example of nucleophilic aromatic substitution, which involves adding a nucleophile to an aromatic ring that has an electron withdrawing halogen as well as other electron withdrawing groups that are either ortho or para to it. The halogen or the nucleophile here is this ethoxy group, which will take the place of the fluoride, which is the leaving group, and we get this as a product. In the last reaction, we're doing a hydrogenation under high pressure of hydrogen and using rhodium, which is a very reactive metal, to reduce the double bonds in the aromatic ring and produce a cyclohexane product. The last thing we'll do for this chapter is do a synthesis example involving benzene and converting it into this tri-substituted product. In this synthesis example, we want to add three different substituents: an acyl group, which would involve the Friedel-Crafts acylation, a bromine, which would be bromination, and a sulfonic acid, which is sulfonation. One of the things you might recall from this chapter is that Friedel-Crafts alkylation as well as acylation is hindered by electron withdrawing groups, such as a sulfonic acid. So we want to make sure we add this acyl group first, or at least certainly before we add the sulfonic acid. So if we start off with the Friedel-Crafts acylation, we could add the acyl group. This is an electron withdrawing group, so it's a meta-directing group. So if we add the sulfonic acid next, we can add it to the meta position. So sulfuric acid and heat will lead to that. And then lastly, we can add the bromine to this position. Now this intermediate actually has two electron withdrawing groups, so it would be a very difficult reaction, but if it does occur, it should add the bromine to the meta position of both of these two substituents.